In this video, I want to focus on some of the applications of Taylor series. We've kind of talked about the point of them, that they're meant to approximate functions, but this leads us to the inevitable question of how good are they at approximating functions? So how accurate are these approximations? So if the main point of a Taylor series is to approximate a function, how good of a job does it do? How accurate is it? Well, one of the main tools that we can use to answer this question is something called Taylor's inequality. And Taylor's inequality is a theorem that says the following. It says that if the n+1th derivative of x, of f with respect to x, so f n+1 of x, if that is bounded by some value m, and we're doing the absolute value, so we're basically restricting how big this n+1th derivative can be on some interval. So let's say for all the points a radius d away from the point of interest, if we're centering this at some point a, and it has a radius of what we're calling d here, this is sort of our little interval where this is true on. Then it turns out that the remainder, which we're going to call Rn of x, this is the notation we've used in previous videos, of the nth degree Taylor polynomial, satisfies the following. So basically what we're saying is we're using an nth degree Taylor polynomial, so we're truncating our thing after the nth term. And this Rn of x, the remainder, which you can think of as essentially the error, how far off it is from the real function that it's trying to approximate, is as follows. That remainder term is going to be less than or equal to m over n+1 factorial times the absolute value of x minus a to the n+1th power, for all the points that are in that interval of interest. So they're on that original interval. This is kind of a complicated idea. I want to go through sort of a proof-ish, because the proof gives you some intuition for why this works. And we're just going to look at the case where n is equal to 1, and also we're really going to restrict it to an interval. Basically, we're just going to look on basically one side of this thing. You can think of it as being an interval centered at a, and we go a distance d to the left and a distance d to the right. You can prove it for more general cases, but it's going to be easiest if we're also only looking at these values. So we're going to only consider the values of x to the right of the center point a out to a distance d, so from a to a plus d. You can do it on the interval from a minus d up to a as well, but and you can generalize this to higher powers of n, but that's all a lot more complicated. So basically what we're saying here is we're going to use the Tn where n is equal to 1, so T1, we're doing a linear approximation. So this is a linear approximation. And we're asking how much error does our linear approximation have if we go out a certain distance from the point that our Taylor series is centered on. Okay, so what we're going to do is say that on this interval, we are going to assume that our n plus 1th derivative, so when n is 1, the n plus 1 means we're talking about the second derivative, so f double prime of x is less than m on that same interval. So we've got a bound in what this derivative is. What that means is if I were to integrate both sides of this inequality, and I guess I should say less than or equal to, that's what our theorem technically said. So if I integrated both sides of this, and really I guess I should be doing, because we want the result to be in terms of x, I'm going to use a dummy variable here. Let's use t. And I'm going to go from a up to x, where again x is on this interval that we were talking about right here, that this is equivalent, or not equivalent, I'm sorry, less than or equal to doing the same thing to the m on that same interval. So essentially all I'm doing is integrating both sides of this, where I've introduced a dummy variable. We're integrating from the point that we're centered at up to some arbitrary x value, as long as that x is somewhere on the interval where we have this bounded behavior occurring. So if we integrate both sides of this, on the left, we're integrating a second derivative, and the result is that we get a first derivative. And we can plug in the two bounds. We'll get f prime of x minus f prime of a when we evaluate this thing, the integral of this, at the two bounds. And that's going to be less than or equal to this other one over here. M is just a constant. It's the value that we said the second derivative must be less than. And so I have this value of m. We're integrating with respect to dt. So I'm just going to get mt, plug in the bounds. So we get, if you want to think about it like this, mt evaluated between a and x. This whole thing is just going to give me m times x minus a. So this is the relationship that we've got. This difference between these first derivative terms has to be less than or equal to m times x minus a. Okay, so why do we care about this? If we rearrange some terms, notice that this f prime of x, I'm going to add the f prime of a to both sides, is less than or equal to f prime of a plus this m times x minus a. And what we have here is the equation of a line. And in a sense, you can almost think of it as sort of the linear approximation of the derivative, where this m is some bound on how steep the slope of this line can be, but we have a bound on that steepness from up here. So here's an equation for what f prime of x can look like in this regard. If we go ahead and continue this process, basically I want to integrate again, do the same thing. So we want to integrate from f double prime all the way till we get back to f. So I'm going to do the same thing here. I'm going to integrate from a to x of f prime of, we'll just change that to a dummy variable. And that has to be less than or equal to, now we're going to integrate the other side of this whole thing. F prime of a, that's some constant, plus m times x minus a, and I need to change that x to a t again, so we're using our dummy variable here. Do the same thing over here. When we integrate f prime, we're just going to get f, and when I evaluate it at the two bounds, it's just simply f of x minus f of a. And that has to be less than or equal to, integrating this piece over here, we're going to get f prime of a, that's a constant, right? There's no dependence on x, or in this case on t here. So this is going to be f prime of a times t, and then when I evaluate at the bounds, I will get f prime of a times x minus a, in the exact same way that evaluating between the bounds here gave us this x minus a. The same thing is happening here. For this term, this one does have a t dependence, so when we integrate it, we have to actually integrate that factor of t. So let's integrate this one. Let me just write it explicitly as a separate piece here. and let's do that integration. So for now, all we're doing is integrating this back to be in terms of the original function f. Okay, so let's do this integration. The only dependency, remember this m is just multiplication, m times this thing. So here's my only factor that I have here. It's the factor of t. So you could think of this as, if you wanted to, mt minus ma, and you could integrate both of those things. And depending on kind of how you want to do this, or you could even do, might be even easier to do a u substitution if we want, doesn't matter. But I'm going to integrate this first piece here. So when I integrate mt, the integral of t is going to be 1/2 t squared. So I'm going to get plus mt squared over 2 minus ma times t. And this is being evaluated between a and x. And so I'm not going to bother to rewrite this left-hand side a whole bunch more. Let's just say this is all the same, this is all the same. Let's plug in the bounds over here. So I'm going to get mx squared over 2 minus ma times our x value. That's sort of the upper bound plugged in. And then from that, I'm going to subtract off the lower bound where we plug in the extra factor of a. So this is going to be ma squared over 2 minus ma squared. That's just plugging in the a into t in both locations. And this is going to wind up just being a constant, right? ma squared over 2 minus ma squared. So I have a half of an ma squared minus a full ma squared is going to give me a negative half of an ma squared. But then I'm subtracting that. So I'm adding a 1/2 ma squared. And we get mx squared over 2 minus max plus ma squared over 2. And this piece here may not be obvious right at first glance, but that thing is a foiled out perfect square. And so this thing is going to look like, if we write this out, maybe the easiest thing to do is just, let's basically factor the 1/2 out. So you could think of this as a 1/2 times mx squared minus 2max plus ma squared. And notice I've basically just factored the 1/2 out. If you were to distribute this half back through, you'd get exactly what we've got right here. So again, I'm not touching any of the rest of this yet. But the whole point of this is, and you could also factor the m out. I should have done that as well. So let's just go back and do that as well. Let me factor the m out and just say that's gone, and that's gone. And what we wind up inside inside of these is simply x minus a quantity squared. So this is just going to be m over 2 times x minus a squared. So this is the result, again, of simply factoring this perfect square out. It looks like this. So let me put all these places where I just was copying stuff down so we have the whole thing on one line. What we've got now is f of x minus f of a is less than or equal to f prime of a times x minus a plus m over 2 times x minus a squared. So again, not necessarily intuitive why we're going this way, but all we're doing is integrating enough that we get things back to be in terms of the original function f. We started with f double prime because we were doing a second order with n equals 1, our value, with n equals 1, we're doing a first order Taylor polynomial, and the first remainder term involves an f double prime. So the first piece of the remainder, and we're just integrating everything back up to sort of where we started with. Okay, so if I move this term over to the other side, so I'm just going to do some algebra, we have f of x minus f of a And I'm going to do this in parentheses. Minus f of a plus f prime of a times x minus a for expediency. When I pull this term over to the other side, it'll have a negative sign, but I'm basically factoring that negative sign out of both this term and the negative sign that'll be in front of this term and grouping them together. And that's less than or equal to Rm over 2 times x minus a squared. So we're actually getting pretty close at this point. What I want to point out now is that what we've got right here, this is our first degree Taylor polynomial. This is our Taylor approximation of the original function. And so what we're saying is, if I look at the difference between the original function f and our approximation of f, which is in this case a first degree approximation, t1 of x, that gives me the remainder. But we have a bound now that the remainder must be less than this term over here, m over 2 times x minus a squared. So we have a bound now on what the remainder might be. By integrating the original, so here was our original requirement. We just needed a bound on the second derivative. We integrated twice to get back to the original function f. And if we have this bound on the second derivative, here's how it plays out when you look at the net effect of what that same constraint does when you are now have integrated twice and are dealing with the original function. We separated everything out so that we have this term here. This is literally our approximation. This is our first degree Taylor polynomial right here. And we're looking at the difference between the original function and our first degree approximation, which is sitting right here. That is what we call the remainder, R1 of x. So the remainder is just the difference between our approximation and the actual function. And we have a bound on it. This bound came from this original bound on the second derivative. All we did was integrate enough so that we could see the net effect of what that constraint on the second derivative looks like by the time we get to the original function. You can do this in more generality by starting with, maybe we have the case where n equals 2. And so we would need to have a bound on the third derivative, and we would need to integrate 3 times to get to the original function x here. And we would have a new constraint over here, but that new constraint over here would be the result of integrating 3 times, and it would in general take the form of what we've got right here. Notice in this case, that's exactly what we've got. M over 2, because our value of n was 1, times x minus a squared, again, because n was 1. So that is our constraint. And this is the idea behind the constraint. We start off with some constraint on the n plus 1th derivative, and then we integrate n plus 1 times to see what the net effect of that constraint is by the time we get back to the original function. And it turns out the way that things compound when you integrate multiple times is we wind up with a formula that looks like this one here after 2 integrations, and in general looks like this one here after n plus 1 integrations. So this is the idea. That's it. If that doesn't help, it's not super important to have the y down. We just need to be able to use this. So let's put it to use in just a couple of quick examples. I don't want to do a ton. Maybe we'll do 2. So let's say, let me find the one I wanted to do here. I want to, here we go. I want to come up with maybe a second degree approximation of, say, the square root function. So I want to approximate y equals the square root of x with a second degree polynomial. And then using that approximation, and let's say we want to do it at some point. Let's say at x equals, I don't know, 3. How accurate is this approximation when maybe we're a radius of 1 from that point. So when we're go between 2, let's say between 2 and 4. Okay, so you can think of this as sort of two parts. So the first one is that we want to approximate our function. If you remember how we do that, the formula for our Taylor approximation is going to be that we basically do f of a plus f prime of a times x minus a plus f double prime, f double prime of a over 2 factorial times x minus a squared plus dot dot dot. But for us, because we're only doing a second degree polynomial, we're going to get rid of the dot dot dots, and instead of calling this an exact equal sign, we're going to say this is our approximation. And so for us, our value of a is 3, because that's where we want to center our approximation. Okay, so for us, what we're suggesting is, notice I'm going to need f, f prime, and f double prime. So let's look at all of those. We already have f of x. It's the square root of x. What is f prime of x? Well, what's the derivative of the square root of x, or alternatively x to the 1/2? It's going to be 1/2 x to the negative 1/2. And when we do the second derivative, I will get this factor coming down again. So I have the 1/2 times a negative 1/2. It's going to be negative 1/4 x to the negative 3/2. The power goes down yet another power. And so this is what we've got. So this is what we're looking at. I also am going to want, in order to determine the accuracy using the theorem, notice that we need, this theorem applies to the n plus 1th derivative if we're using a degree n approximation. So I actually also am going to want the third one. I don't need this third degree derivative in my approximation. I need it to approximate the error. So let me say that here. For the error, I will also need f triple prime of x. And that will be, I will multiply this 1/4 by a negative 3/2, and again, they're both negative, so the negatives will cancel, and we will get, what, 3/8 times x to the negative 5/2. And this will be used when we talk about basically our error bounds. Okay, so let's put these together. I want to evaluate each of these now at x equals 3. So I want f of 3, I want f prime of 3, and I want f double prime of 3 to get f of a, f prime of a, and f double prime of a. So here, this is just going to simply be the square root of 3. The next one will, depending on how you want to write it, it's going to be a little bit ugly, but we can write this one as, let's say, 1 over 2 root 3. And then this last one will be, what do we get? A negative 1 over 4 times 3 to the 3/2. When we do it to the 3/2, you could think of it as 3 times a root 3. So we could rewrite this as negative 1 over 12 root 3. And I'm fine with keeping these improper radicals where the radicals are in the denominator. Don't care about that. But these are our values, whatever those happen to be. And so our approximation, our T2 of x, our second degree approximation of the square root function here, centered at x equals 3, really should have just picked x equals 4, and these would have looked a lot nicer. Maybe I should do that next time. Anyways, we're doing it at 3, so we have a bunch of radicals left, not a big deal. But it's going to be the square root of 3 plus f prime of a, so this value, 1 over 2 root 3 times x minus 3 plus the second derivative that we had up here is right here. We're going to pick up an extra factor of 2 in the denominator from this, so it's going to be a negative 1 over 24 root 3 times x minus 3 squared. So this is our ugly, ugly approximation. How accurate is it? So there it is. How big is the error? How much error can there possibly be on this interval? And so now we need to realize that basically we want to figure out how big can this value be, the third derivative, on this interval. What's the biggest it could be? And so basically what we're going to do is find the bounds of this on the interval from 2 to 4. How big can this value be? What's the biggest it can possibly be on this interval? So that's all we need to figure out. If we look in and figure out what this value, so this is basically this will be our m that we're going to use for our approximation. So I already know that according to the theorem, our R2 of x, the remainder, this is our error. This error is less than or equal to, in this case, m over 3 factorial times x minus 3 cubed. Okay, this simply comes from our formula right here. So when n is equal to 2, we get a 3 factorial in the denominator, x minus 3 cubed. And that is where this came from. We just need to figure out what that value of m is. So m is the biggest value that this third derivative takes on this interval. So how do we figure out what that looks like? Well, we can actually plug in some of these values. If we note that basically this function here, 3/8 x to the negative 5/2, this ugly function here, it's going to be, so if we plug in the two different bounds, 2 and or 4, the two endpoints, we should get a sense of kind of the behavior of this thing. So let's find m. So all I want to do is plug in f triple prime of 2, f triple prime of 4, and I'm doing this simply because I don't know what the behavior of this function is. I don't really know what it does. So I'm just kind of guessing and saying, let's look at it, see if it's monotonic, and figure out which one of these two ends is going to be have the larger value. So in this case, what we get in the first case is simply 3/8 times 2 to the negative 5/2, but you can again think of that as 3 over 8, and on the bottom that's 2 to the positive 5/2 in the denominator. And notice that because we've got this set up, and I guess we could have even done it back here, maybe this is the easier way to do it. Let's look in total generality. Instead of just guessing the endpoints, I think we can answer this question without having to look at both. Let me just rewrite the original function again. So we have f triple prime of x, but it's going to be equal to 3 over 8 times x to the 5/2 in the denominator. X to the 5/2. This is a monotonically increasing function on the interval that we care about, from 2 to 4. So basically, as long as x is a positive value, this thing is monotonically increasing. Right? This is a power. We're taking x to a power greater than 1. So right, when you square something for positive values of x, it's going to be increasing. When you cube it, it's monotonically increasing. Even when you do it to the first power, it is monotonically increasing. Heck, even if you do a fraction power, 1/2, right, it is still monotonically increasing. So what I'm thinking about is just x to the 5/2 by itself. It is an increasing function, but it shows up in the denominator of this function. So when is this term going to be its largest? When the denominator is at its smallest, right? What's a bigger number, 1/2, 1/3, or 1/4? 1/2 is the largest number because it's when the denominator is the smallest out of this list. So that's all we want here. When is the denominator going to be the smallest? Well, if this thing is monotonically increasing, it's going to be its smallest at the left side when this thing is equal to 2. And that will mean this whole thing will be at its largest at that particular point. So this thing, we need this at x equals 2. That's when it's maximized. And so we will get 3/8 times 2 to the 5/2. If you want to think about this as, because it's 5/2, you could think of it as sort of 2 to the first power, so 2 to the 2/2 times 2 to the 2/2 times another 2 to the 1/2. And when you multiply things with a like base, you just add the exponents and you would get 5/2 here. So really, 2 to the 2/2, that's just a 2. That's just a 2. And this is a square root of 2. So we have 2 times 2, which is 4, root 2 on the bottom. So 3/8 times 4 root 2. That is our bound for this thing. We can simplify it a little bit. So 32 root 2. This is m, the largest value of f triple prime of x on the interval that we care about from 2 to 4. And so that's going to be our value of m, and that means that our error is less than so R2 of x, our error is less than or equal to this number, so 3/32 root 2. And again, all I'm doing is plugging into this formula now. We have our value of m. We're plugging into that. Over 3 factorial times x minus 3 cubed in this case. So here's our bound for basically the error at a given value of x. And so for us, that value of x is stuck between 2 and 4. And we can basically figure out the absolute maximum value here. So, what is the largest value that this piece can obtain over this interval? So that's going to occur at either of the two endpoints. We would get basically a value of 1 here when you get a distance of 1, which we're then cubing. And so this is at most 1 on the interval from 2 to 4. Right? It's always going to be a value between basically 0 and 1 because it's absolute value, so it has to be positive. When you're at x equals 3, you get 0. When you're at x equals either 2 or 4, we're 1 away from 3, and we cube that value and get 1. So at most, this gets up to a value of 1. And so really, this is just our bound over here. And we can see if we try to clean up this ugly thing here, we have a 3 in the numerator, and ultimately we're also dividing by 3 factorial. You can cancel the 3 here with a 3 in this, and we would wind up with 1/64 root 2. That is our maximum error. Our error is less than or equal to 1/64 root 2. And if you want to come up with a decimal approximation of that, I have no idea what that is going to be. Let me see if I've got a calculator handy. Here's one. Let me see if this can do it. So 1/64 times the square root of 2. And so I got 0.011-ish. So our error is going to be less than that. We're not bad. We're almost to the nearest hundredth, just a little bit more than to the nearest hundredth. And so we have a bound on what the error can be here. Let's do maybe one more example. one thing that I talked about is that you can use the Taylor approximations to approximate functions on a calculator or on a computer, like a sine function. So let's just say that we want to do that. Let's say I want to approximate the sine function, and I want to make sure that we're accurate within a certain number of decimals. So let's approximate sine of x and figure out what the maximum error is if we do up to the 5th degree. So I remember this one off the top of my head. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot, 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 dot. So let's say we truncate it at the 5th power here. And let's figure out that, and this is near x equals 0, so centered at x equals 0. Let's use this to approximate some value of x that's close-ish to 0. So use this to give, let's say, the sine of, well, it doesn't even have to be that close to 0. Let's say sine of, I don't know, 18 degrees. It's relatively close to 0. So some angle that's relatively-ish close to 0 in the grand scheme of things. Let's see how accurate we can get this to be. So basically, we can plug in our 18 degrees into this and try to figure out what that's going to look like. But really, the sine of x is typically done with regards to radians. So we probably should convert this to radians before we plug everything in. So what is 18 degrees in terms of radians? Hopefully you remember the conversion. If not, we can do that real quickly. Basically, you want to think of what fraction of a full circle this is equivalent to. So you can think of it as like 18 degrees out of 360 degrees should be the same as essentially the x value we're interested in. Let's call it, I'll just call it r, the number of radians that we're interested in out of 2 pi. And we basically do our cross multiplication, and we get that, let's see, 360r is equal to 2 pi times 18, and then we divide by the 360 on both sides, and we get simplification. That 360 is always going to cancel with this 2 to give us a 180 in the bottom. And this works out really nicely. 18 over 180, we're going to get a factor of, in this case, pi over 10. So pi over 10 is approximately 0.314, right? We just moved over our decimal a little bit. So 0.314-ish. Okay. And let's figure out then, after we're done giving our approximation, let's figure out how far off this approximation might be. So here's our value of x that we're going to plug in to here, and we're going to get that the sine of 18 degrees, which is the sine of pi over 10, is going to be approximately equal to pi over 10 minus pi over, let's write that, pi over 10 cubed over 3 factorial plus pi over 10 to the 5th over 5 factorial. So that is our approximation. And we can simply plug this into a calculator. Again, let's see if mine has any juice left. So all I'm doing is plugging these numbers into a calculator. My battery's about to die. Let's see if we can get through this problem before it dies. So pi over 10 plus pi over 10 cubed, and then divide the whole thing by 3 factorial. And oops, that needs to be a minus sign. I'm subtracting that, not adding. Plus pi over 10 to the 5th power divided by 5 factorial. And when I hit enter, this gives me approximately 0.3090170542. If I do the actual value instead, if I just simply do sine of pi over 10 on my calculator in radians here and hit enter, I get the actual value is, let's see, approximately 0.3090169944. These are pretty darn close. So we can see just by observation that we're getting an answer that's close. How would we know without having a calculator to spit this number out? How would we know how close we were here? Well, we could figure out our error. So let's say that in this case, because we're approximating a value that's about 0.3, a little more than 0.3 away from x equals 0. Right? This is our approximation near x equals 0. We're not exactly at x equals 0. We didn't plug in sine of 0 degrees. We plugged in sine of 18 degrees. So we're a distance of about 0.3. Let's just say 0.4 to be safe. So what is the max error on the interval from negative 0.4 up to 0.4? Because certainly the value that we found is somewhere within that bound. And it's going to be, according to what we've got, our error bounds are right here. So we're going to have our, you could think of it as, in this case, R7 of x. You'll notice that we only went up to the 5th power here. So you could call this R6, but there are only odd powers anyway. So we're actually going to be able to bound this with the 7th power term because there is going to be no 6th power term. So we can use 7 for our value here because we know that it only has odd values anyway. So our next derivative would be the 7th derivative term with the 7th power term showing up here. So our R7 of x in this case, we can bound this. It's less than or equal to m over 7 factorial times our distance x minus 0 up to the 7th power. But the x value, this is going to be a maximum of 0.4, right? Because that's the bounds of the interval that we're interested in. And so we're really looking at something that's m times 0.4 to the 7th power over 7 factorial. And if we plug that into the calculator, so 0.4 to the, that's a really ugly 7, but 0.4 to the 7th power, let me do that, 0.4 to the 7th, and then I want to divide that by 7 factorial, so 7 factorial. I get a tiny, tiny number. So this is equal to m times our value, which is 3.25-ish, roughly, times 10 to the negative 7th. So this thing is right here, basically 0.0000, bunch of zeros, 325, dot, dot, dot. Now we just need to figure out what the maximum value of m is on this interval. And what is m? M is the largest that the 7th derivative of the original function, sine, is going to be. And if we want to just play it safe, we could probably get something a little bit more accurate than this. But keep in mind, when you take derivatives of the sine function, you only get back sines and cosines. And if you think about the derivatives of that, you're going to get more sines and cosines. And when you start thinking about what do sines and cosines evaluate to, what is the biggest a sine or cosine function could be? Because basically we're saying we're taking the sine function, we're taking the 7th derivative of it, and that'll get us back to either a sine or a cosine with a plus or minus sign on it. What's the biggest that could possibly conceivably be? 1. And it's probably going to be less. But who knows? This is 1 at most because f7 of x is going to be either a sine function or a cosine function. If it was 8, we'd be all the way back to the original sine. So I think this will be, what, like negative cosine of x? What's the biggest that this can be over any values of x? At most, this is ever going to be 1. So just keep that in mind. So if we then further restrict it to this interval, we might actually see that it's something different. But no, I think it is going to be 1 in this case. So really, but basically what we're saying is our answer should have been accurate all the way up to doing anything that is 0.4 radians. So 0.4 radians would be a bigger number than we use. We use 0.3 radians, 0.314 radians, right? Pi over 10 radians. But that our answer should be within this accuracy. And you'll notice, sure enough, it looks like it is. We've got basically essentially, these things differ. This one is 0.70 down here and 0.69 when we compare those same two decimals. So we've got 5 decimal places of agreement, and then these ones are really only off in the, let's see, what decimal place is that? 1, 2, 3, 4, 5, 6. They're off in the 7th decimal place, basically. That's essentially, depending on which way this one would round. If you were to round this to 7 decimals, it would round to the exact same number that we've got here. So this is a sense of how accurate these things can be. You can see you don't necessarily need a ton of terms to get an accurate approximation, as long as you're staying close to whatever point your function is centered on when you center your Taylor approximation. So this is one last thing that I wanted to take a look at. And if we wanted to try to pick a further value of x out to go, maybe we want to see, maybe I only want to be accurate to 5 decimals. How could I figure out how far out in x I could go from 0? Right, we were able to go up to 0.4 here and be within this amount of error. What if I cared about having less, or I was allowed to have more error than that? What if I wanted to be within 0.0001, right? So 10 to the negative 4th instead of something on the order of 10 to the negative 7th. How much further out could I go? Well, I'm accurate all the way out to 0.4 within 10 to the negative 7th times a factor of 3 here. So certainly within 10 to the negative 6th. What if I only want to go out to 10 to the negative 4th? How big could I make x and still be within this? All I would need to do is come back to the formula and remember that it's basically saying our formula m, which is going to be 1 over, in this case, we've got our 7 factorial, we've got our x minus 0 to the 7th. Here's our formula, and we want this error to be less than 1. Well, we already know that this m is at most going to be 1, so you could think about this as basically being x to the 7th over 7 factorial. What values of x will allow this to be true? And we can actually figure that out. We can multiply both sides by 7 factorial. That's a big number. Let's see. Let me do 7 factorial here. Come on, calculator, stay on. So 5040. So if I multiply both sides by 7 factorial, I'll get that x to the 7th is less than 0.0001 times 5040. When I multiply that by my 0.001, I get about a half. And then if I want to figure out what x is, all I need to do is take the 7th root of that number. And we can do that. And I get that this goes out to about 0.9067, ... So I can get all the way out to almost 1 radian away, 0.9 radians away from 0, And I'll still have an answer that's accurate within 10 to the negative fourth. We can figure out, basically, I don't have to restrict myself to this domain from negative 0.4 to 0.4 radians around the zero. I could go all the way out to 0.9 radians from zero and still be accurate within this amount right here. So this is kind of a cool way to get a sense of exactly how big your error is going to be based on the number of terms that you've included. And this is the main thing I wanted you to take away from sort of the applications of Taylor series. There are others, and in fact, it might be worth, if you're interested, reading section 11.11. It goes into some of the physics applications. There's a ton of applications related to computer science and scientific computing where you are trying to model physics type behaviors, differential equations, and so on a computer. And a ton of analysis with Taylor series comes into play to get those types of models to be computed accurately on computers. So there's a lot more, but for now, I really wanted to focus on the idea of error. How big is your error going to be based on how many terms you include in your approximation, and how far are you going from the value of x that your Taylor series is centered at. So hopefully this gives you a little bit of sense of kind of how that can all work, and hopefully it will help you get through the couple of homework problems if you want to do them for extra credit from this section.